Hi everyone, in this video we'll be going through root mean square values, or as it's more commonly known, RMS values. The thing to know about RMS is that all AC voltages that you see around the world, they're all given in RMS values. So whenever you see something is X amount of volts or X amount of current and it's talking about AC, then that thing is referring to the RMS value. So for example, here in the UK, our mains power is 230 volts. Now that's not the peak, that's not the maximum amount of voltage that enters our house, but that's the RMS value. So the peak voltage of that is actually about 325 volts instead. One thing to note as well is if you feel like there's anything in this video that I skipped over, then I'm only skipping over it because we went through it probably in the last video or a few videos before. So if that's the case, go click in the description or in the comments, go onto the playlist and watch the other videos, because if I've skipped over it, it's because it's now considered basic, right? So first thing we're going to touch on when we're discussing RMS is we're going to talk about average versus RMS. So sometimes you could be easily mistaken to convince RMS values for average values, but they're not. The reason being is because we discussed this in the last video as well. We would never use the average value of a full cycle of a sine wave. So let's take a sine wave here, right? So we've got a sine wave here. All the positive values up here, right? They're going to be cancelled out by these negative values. So if we average out all of the values along this sine wave, it's going to be equal to this 0, right? So we never ever use the average value of the full sine wave. However, sometimes we do use the average value of the half cycle. So for example, we might take the average value of this half cycle, the positive side, or we might take the average value of the half cycle of the negative side. Okay, so those two things can actually be useful to us, but the average value of the full cycle, definitely never going to use it. Okay, all right, so what is RMS, right? We need to find the DC voltage equivalent of the waveform. That's what we're really interested in. We're really interested in what can we say that this voltage, this waveform is in volts, right? A sine wave is going to go from 0 up to a value and then fall back down to 0 and then come, go to the reverse value, the negative side, positive side, and then come back up to 0, right? So that's what a sine wave is going to do. So what we could do is we could just say, okay, well, at this point here, the sine wave is 5 volts. And at this point here, the sine wave is 5 volts. Or at this point here, the sine wave is 12 volts. That's just, it's pointless finding out the voltage value of one particular point of the sine wave, right? So we want to know, what does all of this voltage across the whole sine wave work out to be? And that's what we call the RMS value. So we're basically using an averaging scheme to calculate like the effective power dissipation without using any real sine functions or anything. So the averaging scheme that we're using is called RMS, which stands for root mean square. And you'll see why we call it that when we actually get around to doing the math side of this. So we're not going to touch on any math stuff now. We'll do that later on in the video. So let's just get down like an official definition, okay? Okay, so here's an official definition. The RMS value of an AC signal, right, is equal to the value of DC voltage or current, which would have the same effect as the AC. Think of it like this. The RMS value is the AC value that's needed to do the exact same job as a DC supply. So imagine you had a 12-volt battery. So for example, you like the 12-volt battery in your car. That's a DC battery, right? So it supplies a steady 12 volts, right, at its output. So the battery supplying steady 12 volts. If you connected an LED bulb to it, the LED would light up in a steady fashion, right? It would light up and it would stay lit at one brightness. It's not going to dim and then go back. But if you had, for example, the LED connected to an AC wave, and let's say you had, for example, you connected an LED, and so let's say you connected an LED to this waveform here, right? And this was 12 volts, and this was 12 volts. Well, the LED would start off. The LED would start off here at this point and be completely off. As you ramped up the voltage across, it would rise slowly, getting brighter and brighter and brighter until it reached its peak here and was max brightness. And then it would start to get dimmer again, come back down over here until it reached its peak, and then it was actually fully bright, and then come back to 0. And it just keep on doing that. It'd go from off to dim to fully bright to dimming again to off, backwards and forwards. So we wouldn't use, for example, a 12 volt AC supply in order to power this LED bulb. So what we're thinking of, the RMS value would be the value of the AC power source to light the bulb to the exact same brightness as that 12-volt DC. So what we want is we want to try and get like 12 volts across the average, right, of the waveform. So we want to try and average 12 volts across it. So what we're going to need is, we're not going to be able to do that with an AC waveform that peaks at 12 volts. That's not going to be enough. So we're going to have to use a higher peak voltage. So for example, I don't know, like 18 volts or something. And then that will allow us to average out across, the rising and falling of the waveform to get what seems like a 12-volt AC waveform, okay? So when we say that there's 12 volts of AC voltage from this power source, it's not actually 12 volts. We're talking about the 12 volts RMS value. The peak of that is going to be a lot higher. So like I said, when we're dealing with mains in the UK and we've got 230 volts coming into a house, we actually have more than that coming into a house. Like I said, the voltage that enters a house is actually peaking at 325 25 volts. But we're getting an average of 230 volts, which is the RMS value of the voltage that enters our home. Okay, so we're going to talk about how to find the RMS value. We're going to go into the weeds a little bit here, but I promise you it's not going to be long. I'm going to get straight back out of it. So this is going to go it's going to go a bit deep, but don't worry about it. We'll come straight back out and we're going to go after this bit. We'll move on to conversions and it, working out actually what we're doing is just so that you have the idea in your brain of what we're doing. You don't need to memorize these steps and learn it, because there's really really smart people out there that have actually gone and taken these really complex things and made it super easy for us to do it instead. So I'm going to show you the easy lazy man's way to do it all, and it's completely accurate and completely fine as well. So let's just go into the weeds a little bit here and then we'll come straight back out. Don't worry about it. Honestly, you don't need to memorize any of this stuff. The first time I saw all of this in my lecture, I completely turned off. I was just like, what the hell is this? But it's not that hard at all. Okay. So in order for us to find the RMS value, let's say we've got this waveform here. We'll take a bunch of instantaneous values. Usually we'll do 10. Okay. So we'll take those 10 instantaneous values. Now think about it. This is where watching the previous videos is very, very important. How do we know the voltage values at this point, 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 and this point, and here, for example? How would we find out those voltage values? Well, if you watch previous videos, you should know that we can use the sine of the angle of the point that we're after and multiply that by the peak voltage, and we'll be able to find out exactly what the voltage is at that exact point, right? So for example, if we wanted to find out the voltage here at its negative peak, we know that this is 270 degrees. And we know that the sine of 270 degrees is equal to -1. And so we just do -1 times the peak voltage, which is 12 volts, for example. And then that will give us -12 volts. Okay. If we did the same, here at 360, the sine of 0 is 0 times 0 by 12 gives you 0 volts. And we could do that for anywhere. So for example, if we took this position here up here, for example, to be 45 degrees, if we wanted to find the voltage of that and the peak voltage here was 12 volts, then all we simply have to do is do sine 45 times by 12, and then we have the voltage there. So the sine 45 is equal to 0.7071. We times that by 12, and that gives us 8.485 volts. Okay, and so we can do that for all of these instantaneous points, and then we'll find out the exact voltage at each one of these instantaneous points. So we usually take about 10. Then what we do is we take all of those values, okay? We take 10 instantaneous values, and then what we do is we square each of the values. Hence where the last part of the RMS value gets its name from, root mean square, right? So we square each of the values. Then, if you haven't guessed already, root mean square. We take the mean average of all of those squared values, okay? If this isn't making sense thus far, don't worry about it. I've gone through the painstaking effort to actually go through a whole full example of us working at the RMS value this really long way. But like I said, there's a super easy way to do it. This is just how it's done, technically speaking, right? Okay, so once you've worked out the mean average, then what we do is we take the square root of the mean. And this is where, as you can see, it's the root mean square value. Okay. All right. I'm going to show you an example now of me doing the whole thing in detail. I'm just going to whiz through it super quickly. Basically, I've already done it, and I'll just show you the steps that I've took. Basically, it's just these steps. And we're not going to go into any more detail regarding the maths. There's no need. And more than likely on your lecture slides or whatever you've seen online, it goes into detail. You usually see a square with, like, the sum of equations and stuff like that. Don't worry about any of that. There's super easy ways to convert between them, which we're going to touch on in the next minute. Let me just quickly show you an example of the RMS working it out this long way. Okay, so here we've got a sine wave, right? So what's up? The first step is for us to take a bunch of instantaneous values. So we could take 10. Let's say if we take 10 from this side and 10 from this side, there isn't actually any need for us to take the instantaneous values from this bottom side here. The reason why is because if we just take them from here, then it's just both sides of these are symmetrical across the time axis, right? So if we're going to take 20 values and then do the mean of those 20 values on this side are going to match exactly to this side. And to prove it, I've kind of gone through the painstaking effort of doing all 20 of them. So yeah, if you enjoyed this video and it helps you, leave a like, please. Okay, so I've labeled 20 points here with in the orange, as you can see. Then I've got all of their degree points. So 30, 45, 55, 60, 90. You can do whatever you want. It doesn't really matter. Like you could take a whole bunch of points every 5 degrees. Just make sure that you're consistent on this side as you are on this side, because that will mess you up. You don't want to, for example, do a point every 5 degrees here, but then do a point every 10 degrees here. It's going to mess up the mean. So just make sure if you're going to take a degree every 15 degrees here, then do the same over here, right? Anyway, so once we've got the degree values, then what we're going to do is we're going to use the sine of the angle and times it to the voltage peak, right? Which in this case is 20 volts. So by doing that, you get the values for each of the degrees in terms of voltage. So as you can see here, we've got the peak voltage here, 20. So we know that the peak voltage here is 20 volts. You've got the voltage at 180, which is 0. You've got the voltage at 360, which is 0. You've got the voltage at 270 degrees, which is minus 20. And then all of these ones in between, these are all just worked out by the sine of that angle. So for example, the sine of 190 degrees, and then multiplying that by the peak voltage, which is 20 volts. And then same along with all of these. So these are all just worked out by the sine of that angle, sine of that degree, and then multiply that by the voltage peak. Cool. So once we've got these, we now need to square each one of these values. So I've squared each one here. And so as you can see, it goes to 0 here, which is the 180 point, and then it just reverses back 12.04, 12.04, 100, 100, 299.98, 299.98, 353.06, 353.06, and it continues going on and on like this, right? Why? Because the sine wave is symmetrical across the x-axis. And this is why it's important that you take the same distance of values. Okay, so once you've squared each one of them, you now need to take the mean of all of them. So you add them all together, divide them by 20. So for example, these all added together divided by 20 is equal to 206.165. And the last thing we need to do is find the square root of 206.165, and that equals 14.36. which is our RMS value. Now, if you've done this before, you'll probably know that the RMS value of 20 volts, when you do the quick conversion way, is equal to 14.14 or 14.142. Now, there is always going to be discrepancies when you're doing these, because when you're doing mathematical calculations, and this is an important point to know, is that when I was going through and, for example, squaring these, I was rounding off some of these figures, right? And then when I did the mean here, you round off some figures. So figures are constantly rounded off whenever you're converting and doing calculations. You're always rounding off figures. And so when the decimal places or whatever are being rounded up or down, what you're going to get is that you're going to get slight inaccuracies, but it doesn't really matter. So Whether you've got the RMS value to be 14.36 or 14.14, it doesn't matter. The average, you could say, the voltage that you'd expect from a 20-volt sine wave is actually going to be about 14 volts. Like I said, you don't need to learn any of this stuff. All of this long step calculation, they teach it to me in uni, and that's why I'm teaching it to you. You might be tested on it, you might have assignments, I don't know. But this is all long. The much easier way to do it is to just do super basic conversions, which we'll touch on now. Okay, so if you've got the voltage peak and you wanted to get the peak to peak, super simple, just multiply it by 2. I mean, just think about that. It's really easy to understand. So you've got a sine wave here, right? This peak value here is 12 volts. Well, then what's the peak to peak value? It's obviously this 12 plus this 12, which is 24 volts, right? Super basic. But then tell me, how would you go the opposite way from peak to peak to peak? Hopefully you know this. Obviously, you just half it. If you've got the peak to peak value, if I tell you there's a sine wave here with a peak to peak value of 30 volts, you know that the peak value of it, of a positive and negative, is going to be 15 volts, right? So all you're doing there is just multiplying by 2. Nice and simple. All right, so here's where it really gets fun. I mean, if you have the voltage peak, if you want to work out what the voltage RMS is going to be, instead of doing all that long step equation, taking 10 instantaneous values or 20, and then, converting them into, into voltages, and then squaring all of the voltages, and then calculating their mean and taking the square root, forget all of that. If your voltage peak is equal to 20 volts, then all you have to do, if you want to find out your voltage RMS, you just take the voltage peak and times it by 0.7071. And that's going to give you, let's use our calculator. So 20 times 0.7071 is equal to 14.142 volts. And that's it. You don't need to do any sort of long-winded equations, nothing. Take the peak voltage that you have, whether it's, for example, so here in the UK, our peak voltage is 325 volts. You take that 325 volts, multiply it by 0.7071, and that gives you a voltage RMS of 229.8 volts, or obviously in the UK, 230 volts coming into a house. Super simple, right? So in order for you to go the other way, instead of times in, if you have the peak voltage and you want to get to the RMS value, you obviously multiply by 0.707. So the way that I remember that is that obviously the RMS voltage is going to be smaller than the peak voltage. But to get from the RMS voltage to the peak voltage, you simply multiply by 1.414. That's it. So I tell you, hey, here in the UK, we've got 230 volts coming into our house. That's the RMS value. You can say to me, okay, let me times that by 1.414, and I'll tell you what the peak voltage is. So 230 volts times 1.414, and then you get peak voltage of 325 volts. Nice, right? Told you. No complex maths. Nice and simple. All right, then, in the interest of keeping this video a bit short, so here now we've got all the rest of the other conversions. So in terms of the peak to peak voltage, PP, we got a peak to peak voltage. If you know what that is, if you know it's 24 and you want to get to the RMS, obviously you could, half it to get to the peak voltage, and then you could multiply it, or you can just multiply it straight times 0.353, and that's going to give you the RMS value. If you had the RMS already and you wanted to get to peak, you can just straight, instead of multiplying by 1.414 and then times it by 2, you can just times by 2.828. Now, I mean, you don't really need to memorize any of this stuff, and the reason why I'm not going too deep in this, because I don't want you to focus on this. Once you know this, how to get from the peak voltage to the RMS voltage, or from the RMS voltage to the peak voltage, that's all you need to know. The only other thing that you might want to know is, for example, going from the RMS voltage to the average voltage. But they're so similar anyways. So to get from the RMS voltage to the average voltage, you just multiply by 0.9. And if you want to get from the average voltage to the RMS voltage, you multiply by 1.11. So the average voltage is slightly smaller than the RMS voltage. Again, like I said, you don't need to memorize any of this stuff. Just focus on getting this bit concrete, and you can test yourself very easily on this. Check any sort of AC power supply that, or any sort of AC power source that you can, where it tells you the voltage. It's talking about the RMS voltage. Multiply that by 1.414. Find out the peak value of it. Give it a go. I haven't mentioned US in this one, so if you wanted to find out the peak voltage of US, find out what the RMS voltage is that comes into everybody's homes in the US, and then you can just times that by 1.414 and you'd get the peak voltage. Cool. All right, guys. I think this was a fairly easy video. I could see how there's a whole big chunky bit of maths in there, but like I said, ignore all of that. RMS voltage is super easy to deal with. Keep it simple. Times by 1.414 if you're going from RMS to peak, and times by 0.7071 if you're going from peak to RMS. All right, guys. If you have any questions, leave it in the comments below. Please leave a like. I'd appreciate it. And thanks for watching.